The science of artificial intelligence is a multidisciplinary field devoted to understanding and designing systems capable of performing tasks that normally require human intelligence. It stands at the intersection of computer science, mathematics, cognitive psychology, neuroscience, linguistics, philosophy, statistics, and engineering. Artificial intelligence, often abbreviated as AI, seeks not only to build machines that can solve problems, but also to understand the nature of intelligence itself, how learning occurs, how decisions are made, how knowledge is represented, and how reasoning unfolds in complex and uncertain environments. The conceptual roots of AI can be traced back to philosophical questions about mind and mechanism, but the field formally emerged in the mid-20th century. In 1956, a group of researchers gathered at the famous Dartmouth Conference, organized by John McCarthy, who is widely credited with coining the term artificial intelligence. This event marked the beginning of AI as an academic discipline. Early pioneers believed that human intelligence could be precisely described and simulated by machines. Although initial optimism was high, progress proved slower than expected, leading to periods of reduced funding and interest known as AI winters. However, each resurgence brought new methods, stronger computational power, and deeper theoretical insights. At its core, AI is about creating intelligent agents. An intelligent agent is any system that perceives its environment through sensors, processes that information, and acts upon the environment through actuators in a way that maximizes the likelihood of achieving specific goals. This framework allows AI to be applied in diverse domains, from robotics and healthcare to finance, education, and natural language communication. One of the foundational branches of AI is machine learning. Rather than programming explicit rules for every possible situation, machine learning enables systems to learn patterns from data. Algorithms improve their performance over time by adjusting internal parameters based on experience. Supervised learning, unsupervised learning, and reinforcement learning are three major paradigms within this area. Reinforcement learning in particular focuses on training agents to make sequences of decisions through reward-based feedback, drawing inspiration from behavioral psychology. Another essential area is knowledge representation and reasoning. For a machine to behave intelligently, it must store information about the world in a structured way and use logical inference to derive new conclusions. Early AI systems relied heavily on symbolic reasoning and formal logic, building expert systems that mimic the decision-making processes of specialists. While powerful in structured domains, purely symbolic systems struggled with ambiguity and uncertainty, leading researchers to explore probabilistic reasoning and statistical methods. The modern era of AI has been shaped significantly by advances in neural networks and deep learning. Inspired by the structure of the human brain, artificial neural networks consist of interconnected nodes organized in layers. Deep learning models, which contain many such layers, have achieved remarkable success in image recognition, speech processing, language translation, and game playing. The breakthrough of deep learning was made possible by large data sets, increased computational capacity, and improved optimization techniques. These systems can automatically extract hierarchical features from raw data, allowing them to solve complex tasks with minimal manual feature engineering. Natural language processing is another major domain within AI. It focuses on enabling machines to understand, interpret, and generate human language. Tasks include language translation, sentiment analysis, question answering, and text summarization. Advances in language models have significantly improved the ability of machines to handle contextual meaning, ambiguity, and long-range dependencies in text. This progress has transformed how humans interact with technology, making communication with machines more natural and intuitive. Computer vision, robotics, and autonomous systems also play crucial roles in AI research. Computer vision aims to give machines the ability to interpret and analyze visual information from the world, while robotics integrates perception, planning, and motor control to enable physical interaction with environments. Autonomous vehicles, drones, and industrial robots demonstrate how AI moves beyond theoretical models into real-world applications. The foundations of artificial intelligence rest upon a combination of theoretical principles, mathematical frameworks, computational models, and philosophical inquiries into the nature of intelligence. Artificial intelligence is not a single invention or isolated discovery. Rather, it is the outcome of centuries of thought about logic, reasoning, learning, and the possibility that machines might simulate aspects of human cognition. To understand AI at its foundation is to explore the disciplines that shaped it and the intellectual structures that sustain it. One of the earliest foundations of AI lies in formal logic. Philosophers such as Aristotle introduced systematic rules of reasoning, laying the groundwork for deductive logic. Centuries later, mathematicians like George Boole developed symbolic logic, which transformed reasoning into algebraic form. This evolution made it possible to represent knowledge in a structured, mathematical way, an essential step for programming reasoning processes into machines. Modern AI systems still rely on propositional logic, predicate logic, and rule-based inference systems derived from these classical foundations. A second major foundation is computation theory. The work of Alan Turing formalized the concept of computation through the theoretical Turing machine, proving that complex reasoning tasks could be broken down into simple mechanical steps. Turing also proposed the famous Turing test as a criterion for machine intelligence, suggesting that if a machine's responses are indistinguishable from a human's, it may be considered intelligent. This idea shifted the question from can machines think to can machines behave intelligently? Mathematics forms the structural backbone of AI. Linear algebra enables the manipulation of vectors and matrices that represent data. Calculus provides tools for optimization, allowing systems to minimize error and improve predictions. Probability theory and statistics make it possible to reason under uncertainty, an unavoidable feature of real-world environments. Without these mathematical disciplines, machine learning algorithms and neural networks would not function. Another critical foundation is cognitive science and psychology. Researchers studying human learning and perception provided insights that influenced early AI models. Behaviorist theories inspired reinforcement learning, where systems learn through rewards and punishments. Cognitive models of memory and problem solving guided the design of symbolic AI systems that manipulate internal representations of knowledge. AI, in many ways, attempts to computationally model aspects of human cognition, even if the resulting mechanisms differ from biological processes. Neuroscience also plays a foundational role. Artificial neural networks are inspired by the structure of the human brain, particularly the interconnected neurons that transmit signals. Although artificial neurons are simplified mathematical abstractions, the biological analogy encouraged researchers to design layered learning systems capable of recognizing patterns. Modern deep learning architectures, while not biologically identical to real brains, trace their conceptual roots to this interdisciplinary inspiration. Search and optimization theory is another key foundation. Many AI problems, such as pathfinding, scheduling, or strategic game playing, can be framed as search problems within a defined state space. Algorithms like breadth-first search, depth-first search, and heuristic-based search allow intelligent systems to efficiently explore possible solutions. Optimization techniques help identify the best possible outcome among many alternatives, whether in training machine learning models or planning robotic movements. Knowledge representation is central to classical AI. Intelligent systems must encode facts about the world in a format that machines can manipulate. Semantic networks, frames, ontologies, and rule-based systems were early methods of representing structured knowledge. These approaches emphasize symbolic reasoning, where intelligence was viewed as the manipulation of explicit symbols according to logical rules. Although modern AI has shifted heavily toward data-driven approaches, symbolic reasoning remains an important theoretical pillar.